Welcome. So far, we have learned some basics about the refrigeration and the liquefaction methods using the expansion engine and the expansion valve, and we have also done some tutorial to know that how to analyze these systems based on the TS diagram, and we have also found out the value of the this mu JT and mu S, that is the expansion coefficient for the JT expansion and for the expansion engine. Now, we shall be seeing in this particular lecture the applications of these methods for the cryogenic refrigeration and liquefaction in the various natural gas systems. So, here in this particular lecture we shall be learning about these systems: Linde-Hampson refrigeration, Linde-Hampson liquefaction, pre-cooled Linde-Hampson refrigeration and pre-cooled Linde-Hampson liquefaction systems. We have taken these methods in pair because we will find that the basic cycle remains the same whether we are going for liquefaction or the refrigeration. Only thing is this, as we have learnt earlier, that the refrigeration is a closed cycle with a balanced flow, while the liquefaction is an unbalanced flow situation and an open cycle. So, only that differs, but otherwise the basic cycle remains the same. So, let us first start with the Linde-Hampson, and in this series, this Linde-Hampson and the pre-cooled Linde-Hampson, both of these use only the expansion valve for the cooling and not any other engine. So, that is why they have been grouped together. So, we see that Linde-Hampson refrigeration system, sometimes it is also called the simple Linde-Hampson refrigeration system, is basically do not use any kind of expansion engine for cold production, and the cooling is obtained purely based on the Joule-Thomson effect through an expansion valve. Generally, the compression is done ideally as a isothermal process, and as I said that whenever here we find that the compression is occurring. So, as we said that this kind of compression needs the multi-staging maybe in practice, and when the multi-staging is done, we also need the intercoolers, the aftercoolers, etc. to keep the temperature almost constant between the inlet and the outlet of the compressor. And in these cases, for the analysis, we will be considering all the compressors and other heat exchangers, etc. to be ideal. And once we compress the gas, as we show in the figure, that this is these 1, 2, 3, 4, etc., they are showing the state of the particular fluid at different points. So, at this point 1, we are inputting the gas which has to be used for refrigeration, and this is then compressed isothermally, and here we are showing that Q dot, this Q dot is the heat removed to keep the compression isothermal. So, this is a Q dot, and once this is passing through the compressor, it is going to another state 2, and at this state 2, ideally the temperature will be the same as the temperature at point 1, only difference will be the pressure will be increased, and because the pressure has changed, naturally the other properties like the density, like the enthalpy, entropy, all these things will also be changing. And once this is compressed, then what happens? This particular thing is taken to a heat exchanger where this is cooled, and by this cooling we are able to extract the heat, the cold from the this return stream from the liquid reservoir. So, with this particular stream we are cooling it, and after cooling it we are taking it to the JT expansion valve, and here we find that during this cooling the state has now changed from 2 to 3. Now, if we consider the heat exchanger to be behaving isobarically, that is, there is no pressure drop within the heat exchanger, then we will find that the pressure at point 2 and at point 3 will be the same, whereas the temperature will be now less at point 3 than that at point 2. That means T3 will be less than T2. Then once it has come to 3, then we take it for the expansion, and here this particular symbol is representing the valve. So here this is expanded, and after expansion it reaches a state 4 where it is still lower temperature. Now this JT expansion causes a 2-phase to be coming. That means this whatever this vapor was coming, this vapor has been now converted to a 2-phase mixture with liquid and the gas, and please understand that to make the vapor possible, we are trying to cool it down, so that after expansion we can get 2 phases, and this state at this the state at point 3 is the below the critical state, otherwise we will not be able to achieve a 2-phase mixture on expansion. Then what we find that in this liquid space, this particular Q, this Q is coming from the space where we want refrigeration. Okay, that means you can imagine that as if the household refrigerator, whatever heat is there inside refrigerator, that heat is being taken away by this particular liquid. So this particular Q is deciding that how much heat needs to be extracted from the refrigerated space. So once we are taking that quantity of heat from here, and then we find this liquid may get vaporized by taking this particular heat. Now when this liquid is getting vaporized, that means there is a simple phase change, and when there is a phase change, the temperature will not increase. That means ideally this type of a system represents a isothermal heat source for the refrigerant. Okay, so it is not that it has to be isothermal, but as we learnt in our earlier lecture that there can be 2 types of heat sources, and one of them is isothermal heat source. So this we are finding that by vaporization of the liquid, we are able to ensure isothermal heat source. Now after this liquid is vaporized, now this vapor represented by this state G is now taken back, and it is taken through this heat exchanger, as I said earlier. Now they are exchanging the heat, and now what is happening that this particular stream, by exchanging the heat with this hotter stream, is able, means ideally, to attain the same temperature as the inlet temperature at the compressor. So in this particular whole cycle, what we are assuming that there is no temperature drop, that means there is no heat exchange between the system and the surroundings, so that whatever temperature is here, the same temperature is also here, and there is no temperature drop or gain within this particular lines. So these are the assumptions, and because of this all these idealities, what we find that if we do the energy balance, we find that this energy going out from the compressor would be the same as the energy taken in by this liquid. So that is coming from the first law of thermodynamics under all these assumptions. So this is a very simple manner, and the simplest manner one can think of achieving refrigeration by an isothermal source. Now if we want to represent this kind of a system on a thermodynamic diagram, and among the thermodynamic diagrams, you know that we can represent in various ways. One can be the PV diagram, that is pressure volume diagram, and one can be the pH diagram, that is the pressure enthalpy diagram, and another very popular is the TS diagram, which is shown here. That in this TS diagram, what we see that from point 1 to 2, and this temperature axis and this is the entropy axis. So we just ideally move horizontally, and then we reach a pressure, and this pressure at this point is lower than the pressure at this point, as we have learnt earlier in our tutorial how the pressure lines are there on the TS diagram. So we find the pressure is increased isothermally 2.2, and then what happens that we have assumed that there is no pressure drop inside the pipelines, and because of this now the fluid is entering the heat exchanger, and at constant pressure it is getting cooled, and once it has cooled, it has reached point 3, and this point 3 may be adjusted somewhere. That can be the point of optimization, but somewhere we put the 3 so that from point 3, if we expand the gas isenthalpically, and this particular curve is showing the isenthalpic line or the line where the enthalpy remains constant. So, from point 3 we are isenthalpically expanding the gas and we are reaching at some point where the pressure is same as the initial pressure, and that is the reason you can see now that why we need to pressurize the particular gas to a higher pressure. So that we can on expansion we can achieve almost the same pressure as the initial pressure or the inlet pressure to the compressor. Here one should be careful about is this, in practice generally this pressure should be more than the pressure here, because to take care of any of the pressure drops during the travel. So this pressure ideally will be same as the inlet pressure of compressor, but in practice this will not be so. Now once it has gone into this, and this particular dome represents, as we learnt earlier, the two-phase zone. That means within this dome we have two phases, vapor and liquid, coexisting. So once this particular gas has been isenthalpically expanded, now we get two phases, one is the gaseous phase and the liquid phase. Now we assume that the gas and liquid are at their saturated condition, so that this gas will be on this particular curve, that is the saturated vapor curve, where the liquid will be on the this curve, that is the saturated liquid curve. So this is liquid and this is the gas, and this liquid will be now getting vaporized, and once it gets vaporized isothermally, again it will tend to move towards the right. So all these things are not to be shown on the TS diagram, because this phase diagram is just showing the change of the phases. It is not showing the amount. The amount is not shown on the phase diagram, but we have to understand that this liquid will undergo the phase change and it will again move towards the right. Now once this particular vapor is obtained, now this saturated vapor is now being taken back to the inlet of the compressor, and during this taking back, as I said, that ideally we assume that there is no pressure drop in the pipelines, so that the pressure remains constant, whereas this particular vapor gets heated up in contact with the hotter fluid which is coming from point 2 to point 3, and then its temperature is ideally raised to the inlet temperature of the compressor, and this is how we are able to complete a simple Linde-Hampson refrigeration system. Now if we apply the first law of thermodynamics to find out how much heat needs to be taken out from the compressor or has to be given to the evaporator and the work done, we can easily find under these assumptions, like the negligible pressure drop in the pipelines, zero heat leak from the ambient, and we are neglecting any changes in the kinetic and potential energies, then we find this is the expression for the heat exchange. That means the whatever heat needs to be given out from the compressor, and this is the amount of work to be done by the compressor, and this compressor, in this we have also put the overall compressor efficiency. So these two expressions may be used to find out the work done for the overall system, because in the overall system the work is done only at the compressor, and as we learnt earlier, the expansion valve does not involve any kind of external work. Now there are some points to be noted, that in the Linde-Hampson, nitrogen is used as refrigerant if we want the temperature to be between 66 and 115 K, and if we want this kind of temperatures to be varied, then what we need to change the pressure, because as we know that with the change in the pressure, the saturated temperature changes. So if we can maintain the saturated pressure with respect to the temperature corresponding to this within this range, then we can obtain the various types of temperatures, and it is found that for the 66 K, this is the vapor pressure of nitrogen, and for 115 K, this is the vapor pressure of the nitrogen. And as you can see from here, that at 66 K, the vapor pressure is much lower than the ambient pressure, that is about 101 kilopascal. So we find that we need to maintain vacuum to achieve such a low temperature using nitrogen, and that is why we find that lowest temperature is limited by, first is the triple point of the refrigerant at which the refrigerant would freeze. That we know that at triple point any substance would solidify, and then if it solidifies, what happens? There could be the clogging of the pipelines. It will settle on the pipeline, it will cause clogging, and also during this, when they settle, they will put up some resistance to the heat transfer. Okay, so that is why we need to avoid any kind of a triple point approach. And next is this, if we talk of which very low temperature, then we need to maintain a very low vacuum pressure, and this maintenance of the vacuum becomes a challenge, especially at higher flow rates of the refrigerant. So these are generally the two limitations to attain the low temperatures by any kind of refrigerant. And then the highest temperature is dictated by the triple point. Why? Because as I told you that we cannot liquefy a gas above triple point. So we cannot move beyond triple point. We should always have to stay within the triple point of the particular fluid. And then there will be a, as I said, that we are using isothermal temperature source, but there could be a variable temperatures heat source also. And then if we do that, then perhaps we can increase the range of our refrigeration temperature. But in this, if we are using nitrogen, generally it is 200 K is taken to be the limit, and if we want higher temperature than 200 K, then we are using other kinds of refrigerants which are based on the hydrocarbons like freons, and perhaps you know that in that also we have some issues on the achievement of that environmental issues, etc., in using the this kind of freons. Now we come to the Linde-Hampton liquefaction system, and as I told you, the basic method remains the same. And here if you see this, in this particular, again here we are compressing the gas isothermally, and we are ejecting the heat to keep it isothermal. So this point 1 and point 2 will have the same temperature, and then from point 2 to point 3 it's a isobaric cooling, so that there is no change in the pressure, but the temperature is brought down, and then we are taking it to the jetty valve, and on jetty valve we are getting the two phases, the liquid phase and the vapor phase. Again here we are assuming the liquid and vapor are saturated, and this particular liquid is now taken out from the system. And because we are taking out this some amount of liquid from the system, which is given by this m dot f as the flow rate, so that means same amount has to be again given inside the system as a makeup gas. Otherwise, with time, if you do not put makeup gas, what will happen? With time we shall be losing the material from the system. Okay, so this is the difference between the refrigeration and the liquefaction, and that is how it becomes an open system. So I will not go into detail now. Is the same as the Linde-Hampton refrigeration. This vapor is taken, it is now getting heated up by this incoming gas, and the temperature ideally is attained is the same temperature as the inlet temperature to the compressor, and that is how this is done. The work requirement and the this amount of heat to rejected remain the same as far as the total mass is concerned. And here only thing that we are having another parameter, that is the liquid yield. This is another parameter which comes into picture whenever we talk of the liquefaction systems. So this liquid yield will be calculated if we are applying the first law of thermodynamics. We find this is how we find the liquid yield, and it depends on the temperatures across the compressor and also the temperature within this liquid reservoir. And we find that this this H1 and HF, they are generally dictated by the ambient. Okay, because we are taking the things from the ambient and or we are also putting it back to the ambient. So we cannot do much about H1 and HF, but what we can play with is H2, which will, so that we can change the liquid yield. And from this particular equation we see that if we decrease the H2, then we shall be able to increase the liquid yield. So that is what we are saying, that to maximize the liquid yield, we have to minimize the H2 value, and if we want to minimize it, we should raise the pressure. And what we find that by when we are adjusting the pressure at point 2, that is at this point, and we find that the this pressure at the max can go to the inversion pressure. So that is how, that is the limit that we can take it to the at the inversion pressure, because after, if you go beyond that pressure, we can means if you increase the pressure still further beyond the inversion pressure, then we shall be getting heating up, we will not be getting cooling down. So that is the limit, that inversion pressure limit, to so that we can maximize our liquid yield. So this is how we are taking, and here I am shown the work and the this energy transfer, and they remain the same as the simple Linde-Hampson refrigeration system. And one more thing is this: we cannot use this kind of system for helium, hydrogen and neon. Why? Because these three gases have their inversion temperature much below the ambient. So this is also we learnt earlier. So this is not applicable. Why? For these three gases. Further detail about these can be found out from these two books, this Baden and Timmerhaus. Thank you.